Hello everyone, I am your graduate teaching assistant or GTA on Physics 2, and this is our first meeting with GTA. Since this is our first meeting, let me introduce myself. I am a first year graduate physics student at our physics department. So my main obligation or my main task is that to be more useful and helpful to understanding the concepts that covered throughout the semester, and we will also try to solve some useful exercise and the problems on different topics in our GTA meetings. Well, since this is our very first meeting, and since we are a little bit of lack of time because we are starting our first meeting, and even though this is our 7th week, right? 7th or 6th week, I guess 6th week. So we have to be very fast. So first, let's recall from beginning. Well, first thing we need to recall from our previous semester is that what is mechanics? What is mechanics? Can anyone answer to this question? Well, mechanics is basically describes how a system will behave when subjected to some given specific force, right? So let me write it. Okay, I wrote it. Mechanics describes how a system will behave when subjected to a given force. Well, the next the topics that we should know generally is forces. Well, what kind of forces we know? There are basically four main forces that are presently known for physics. Let's list them accordingly. The first one, let's list them according to these forces' strengths. The first one is a strong force. I hope we know this. And the second one, electromagnetic forces. Third one, weak forces. And the fourth one, finally, is gravitational forces. Gravitational forces. Well, maybe someone is already wondering what is other forces. There is a bunch of forces like friction, normal forces, and the chemical forces that holds these different molecules together, and etc. Well, the answer is that all these forces are electromagnetic in nature, in their nature. So relates to this one. Let me write it. Friction and etc. All these everyday life forces that we encounter relates. It's electrical in their nature. Well, except one exception is it's gravitational forces, right? Let me write it, etc. Well, let's briefly describe what these forces do. Well, the strong forces are the forces between protons and the neutrons, or inside atom's nucleus, right? We know what is atom's nucleus. Inside there can be a bunch of positively charged atoms, and these positively charged particles repel each other, and this repulsion force is very strong, and that's why these strong forces hold these protons and the neutrons inside atom's nucleus together. Well, we described it. So what is weak forces? Well, one example maybe to describe weak forces shortly is, for example, describes kind of radioactive decays and some other short-range behavioral forces. That's not important. So weak forces and the strong forces are short-range forces. Short-range forces. So we said this, and well, the thing that why we don't feel these short-range strong forces is that as its name suggests, that it's short-range, right? It's extremely short, so that we don't feel at all, despite the fact that these forces 100 times or more 1,000 times powerful than the electrical forces. but even though they are short range, so we don't feel them. Well, the gravitational forces, finally, the forces that much weaker compared to all other three forces, and even for the because we know that gravitational forces are proportional to the masses, and it's even weaker for such huge objects such as Earth and the Sun and etc. So I hope we all know, we can imagine what these forces are. So the next thing we should describe is that I think there is some good analogy that let's consider these two electrons, right? And they are okay, let's put it as this. Let's be its distance is a Bohr radius, r. So Bohr radius is the average distance between electron and proton inside atoms. So you can think in that way. So if you compute the electromagnetic forces and the gravitational forces, then you will realize that the electrical repulsion between two electrons is around 10 to the 40 times larger than their gravitational forces. So that's why in small scale branches of physics, we can ignore the gravitational forces altogether, since it's very negligible, right? Well, apart from the fact that electromagnetic forces are predominantly, dominating in our everyday life, they are also completely understood forces. The theory of electricity and the magnetism and these electromagnetic forces are completely understood in terms of mass and everything. So this is a very good theoretical model, or how would say, compared to other things like weak forces and the strong forces. The branch of physics that describes these electromagnetic forces is completely understood. This is one thing, right? Well, next thing we should consider is that I think we should cover the history of electricity and the magnetism, little history, so that you will have general ideas, right? Little history. The first thing we should mention is that there was at those early, even in 17th century, etc. People knew that there is, even before that, at early centuries, that there is some kind of, if you wrap this glass and with cat's fur and etc., there is some strange phenomena and etc. So the first history we should mention is that people knew that there is electricity and magnetism, right? Two different kind of objects, and they know that they were dealing with glass rods, for example, or cat's fur, and etc. So, they also knew about bar magnets, their strange phenomena, and compass needles, and what else? Okay, this North Pole of Earth, North Pole, and etc. So people were teaching this electricity and the magnetism. So that there are two different kinds of subjects and etc. So after that, people defined what is current. So what is current, by the way? So we know that current is a charged particles in motion, not particles, charges in motion, right? Generally, charges in motion. In fact, it's electrons that moving around, and that's why they're causing the current. But due to the historical reasons, so we know that current is a motions of positively charged particles, right? Even though we know that it's electrons that moves. Due to the historical reasons, it's current is a positively charged movement of positively charged particles. So we defined what is electricity, magnetism, or different subjects, and we defined what is current. But after that, things started to change. The first one is during 1820, the pupil whose name is Ørsted, I don't know how to spell it, Ørsted, I think you heard about him. He noticed that when electric current, somehow electric current that deflects the magnetic needle. So he noticed that an electric current can deflect magnetic compass needle. So for those people who were living at those years, it was of course like astonishing phenomena. So this was like a starting point. But after that, there is also Ampere. So Ampere noticed that correctly like postulated everything together, that all the magnetic phenomena are due to the electric charges in motion. So he postulated. So while I'm writing, do you know what is postulated? So postulated means that it's not based on the experimental fact. I mean, it's based on the experimental fact, not derived theoretically. So it's postulated means that, how should I explain? I hope you understand what is postulated means, right? He postulated that all the magnetic phenomena are due to the electric charges in motion, or electric current, right? Generally. So after that, even more astonishing result in the history of physics were discovered. It was during 1831. Faraday discovered that moving magnets could generate an electric current, or as we can say that since magnet we have like magnetic fields around it, right? So moving magnets means that changing the magnetic fields could generate an electric current. This was like identical to the case that electric current could generate magnetic fields, right? So Faraday discovered that moving magnets or changing the magnetic fields could generate an electric current, or electric charge in motion, electric current. So I'm just writing these things because these are very general things that we should know. Like if someone wakes you up, and when you wake you up, then you should know these things like inside your brain, that changing magnetic fields generates an electric current, or electric current can generate magnetic fields or magnetic phenomena. It was astonishing result at those years. So generally, we were talking about electromagnetic induction. So these are so-called electromagnetic induction. I hope you already covered this material, or I think you will cover in the next weeks. So after that, history is Maxwell. I hope everyone knows him. Maxwell and some other people, but mainly Maxwell, put everything into compact form and said that electricity and the magnetism can't be separately treated. They are the identical courses in our language, or they are the similar subjects, or they can't be treated separately. I hope you understand what I mean. So electricity and magnetism becomes electromagnetism. So do you think this is it? No. After that, Faraday again. He was very good. Oh, sorry, I didn't write his name correctly. Faraday postulated again. We know that physics consists of full of postulates, especially quantum mechanics is based on the postulates. Is not derived from mathematical things. So Faraday postulated that light is too electric in nature. Well, what is light, by the way? Can anyone answer to this question? What is light? Well, generally we can say that light is the electromagnetic wave. Well, then what is electromagnetic wave? Well, let me just give general expression for that. Let's say that light is propagating in this direction, right? So we have this direction, and we have or generally call it electromagnetic waves. Let's call it electromagnetic waves. What is this? It is there, okay, like this. I hope you understand. Oh, sorry, I should have put this, not this way, but okay, let me put in this way. Oh, sorry, I apologize. How I should put it, huh? Maybe this way. I understood. We see a perpendicular in action, so let me write it correctly. I'm very bad at plotting. So these are perpendicular each other. So let's call it, this is magnetic field. This is electric field oscillating. These two red and the blue lines are perpendicular to each other. Okay, perpendicular. Here we have magnetic field lines. So generally you can see that electromagnetic wave is a combination of like electric and the magnetic fields in the direction of propagation, and they are perpendicular to each other. Okay, because of my bad English, I apologize for you for that in advance. I hope you understand it. So we were talking about what is light, and light is generally, we can say, is one type of electromagnetic waves, and we know from school that these electromagnetic waves are characterized by their wavelengths, right? By their wavelengths or frequencies, wavelengths, so-called electromagnetic spectrum. So we know that there is different kinds of electromagnetic waves, right? X-rays, gamma rays, microwaves, radio waves, and etc. And there is, okay, these are long range, and there is also a visible electromagnetic waves, and whose wavelengths lies between, I think, if I don't forget, nanometers and 700 nanometers. So it consists of visible, or generally called optical range. Consists of 7 colors. So this is a type of electromagnetic waves that we see, and that's why it's called optical range. And I hope that in school we studied that optics, right? So Faraday, we were talking about Faraday, that after Maxwell putting these two, electricity and the magnetism, into electromagnetism. Not putting, I mean, it was from step-by-step history, but after that he made it into compact form. After that, Faraday postulated that light is also electromagnetic in its nature. So this optics, I mean optical range or general electromagnetic waves are also, we can see that electromagnetic in its nature. So we discovered that light is also electrical in nature. Well, after that we have that electricity and magnetism plus optics. These three main branches of physics combined into one simple electromagnetism or electrodynamics. Some people call it electrodynamics or magnetism, because all the electromagnetic waves enter this one, since optics is just one type of electromagnetic spectrum or lies. So we just generally call electromagnetic waves. So why it's complete and a successful theory? Well, a very decisive experiment that proved the Maxwell. So after that, Maxwell put everything into a compact form. That experiment decisively confirmed Maxwell's compact form. Not Maxwell's. Okay, let's write it. All this up to this point, all this electromagnetism. So decisively confirmed electromagnetism in 1818, I think it was 1889 or something like this, by Hertz experiment. So we have complete and very successful theory in our physics compared to other branches of physics, for example, gravity or etc. Not gravity, for example, general relativity. So people will in future maybe decisively confirm this Einstein's general relativity by experiments. But we have this successful theory, right? Electricity and magnetism. So let's maybe talk about its applications. Okay, let's go to this electromagnetic induction. We said that changing magnetic fields generates electric current, or electric current generates magnetic field, right? This is the main principle behind all this. For example, in mechanical engineering, based on this simple fact, right? Changing electric fields generates magnetic fields, right? And vice versa. So this is the main principle that I think if you understand this from very simple things, then you can easily accept other forms of concepts and laws in your future courses. That's why this is very useful course. I know that professors also talked about this, but let's just review all these things that we will cover. So in the next meetings we will cover some interesting examples. Now in this our first meeting, let's consider hydrogen atom as an example. It's very beautiful. So first I'm going to ask is that, okay, we know that hydrogen atom consists of positively charged nucleus, right, proton, right, and there is electron. Okay, revolves around it. Okay, let me write. Revolves around it, electron. So what is for example, net charge here? Net charge of this system. Okay, we are considering this. These are static case. These are not moving. So net charge is zero, right? Absolutely, net charge is zero. So that this positive charge and the negative charge will cancel each other, the fields, so that we have net zero charge. But let's consider this a real example, like in real life. So in real life, we know that this proton undergoing some very non-understandable and random random like perturbations or oscillations, but generally we can consider as it's like not moving, okay, stationary. But electron is moving with the speed of almost relativistically with the speed of light. So what will happen in this case? Can anyone answer to this question? Well, if we consider, if we know that, if you studied electromagnetism, we know that if charges are moving at the speed of light, then it generates these electromagnetic waves or electromagnetic radiation, generally called, as we discussed above. So it will generate and it will end up all its energy, and eventually it was going to collapse. I mean, since they are different charges and they should collapse to each other. I mean, so but in reality it's not the case. So people couldn't explain this phenomena properly. All the fields, classical field physics, couldn't explain this. So here comes, in order to explain this, that there comes quantum mechanics, right? And I should call you that quantum mechanics is based on this only empirical or experimental facts. People couldn't accept these probability things and everything, because quantum mechanics is a probabilistic theory, right? So, for example, like great physicists, for example, even Albert Einstein, that said that it's not complete theory. It has to be modified, but in reality, that quantum mechanics decisively and confirms all the experimental facts, and it's also good established theory, even though it's probabilistic. All the, like, for example, even in your phones, transistors, right? These transistors are made up from, for example, silicon semiconductors, right? Or silicon atoms. So all this, all your electronics are based on the laws of principles of quantum mechanics, so it works, so don't worry. The thing is that how quantum mechanics postulated that even the quantum mechanics can't explain. He just says that even though here is positively charged electron and negatively charged, positively charged proton, negatively charged electron, even though they are moving at this one at high, like relativistic speed, quantum mechanics says that postulated that total energy of the system, or we call Hamiltonian, is conserved quantity. So conserved total energy. So here comes the conservation of like maybe energy in quantum mechanics, but we know that. So he says that this energy of the this closed system or quantum system is conserved. So in specific energy levels of these atoms, it will not radiate any electromagnetic waves. It will be stationary. It will radiate electromagnetic waves or a portion of electromagnetic waves or portion of this small energy or photons only if electron excited to, if only electron decays from high excited state to lower state, and if electron goes to upper state, it will absorb some energy. And all this, like for example, Compton effect, or photoelectric effect, which Albert Einstein explained, photoelectric effect. Everything comes from this basic principle that if electrons goes to upper level, it will absorb some energy, which is equals to h mu. That, okay, generally maybe we didn't cover it yet, but it's worth it. It will absorb this portion of energy, or if we will go from excited state to lower state, it will radiate this electromagnetic wave whose energy is quantized. I mean, not quantized, it's this portion of energy, we will call it, right? So I hope everything now I tried to explain clearly, that this thing, why doesn't this collapse it? Because it's total energy conserved. It's just a postulate from quantum mechanics, and this postulate is much more strong. I mean, nowadays modern physics is based on this postulate, right? Even though people can still like completely describe it, we just said it's postulated, and everything nowadays theory, everything is based on this simple postulate. I hope everything is clear. We just covered some basic general overview. From next week, I hope that I will try to cover some useful exercises and according to your topics that covered in these specific weeks. Since this is our first week, we just covered, we just tried to review all the basic things that we should know. So then see you next week. Hello everyone, I am your